The first thing to notice about this problem is that you've got logs on both sides. Right? So we can use the law of logs that says if the base is the same, which it is here, then the inputs must also be the same. They don't look the same, right? 2n plus 5 does not look the same as negative 3n. But since the bases are both 17, that means that we know that 2n plus 5 equals negative 3n. The rest of solving this is simply algebra 1. We combine like terms. The additive inverse of 2n is negative 2n. We need to maintain equality, so we do the same thing to both sides of the equation. So we get 5 is equal to negative 5n. The multiplicative inverse of negative 5 is negative 1/5, or dividing by negative 5. And we end up with n is equal to negative 1. Once we have that answer, it's a great idea. It's very important. In fact, you'll see in later problems in this set, it's a good idea to plug it back in, evaluate each side of the equation to make sure that the solution you just obtained is not extraneous. So I usually go over here and I'll say, okay, let me just see if n is actually equal to negative 1. So I'm going to say, okay, log base 17 of 2 times negative 1 plus 5. Is that equal to log base 17 of negative 3 times negative 1, right? So I'm evaluating each of these when n is negative 1. So I get log base 17 of 3, and I'm checking to see if that's equal to log base 17 of 3. Nice, it is. Therefore, n is equal to negative 1. So I've found that n was negative 1 via algebra. I've substituted back in. I've evaluated both sides to show that that solution is in fact a correct solution.